begin to introduce Elia Scudiero. He went to UC Riverside as a postdoctoral researcher from Padua, Italy in 2014, and he became an assistant research agronomist in 2018. He studies properties of soils such as salinity and water content to increase the economic and environmental sustainability of farms. Scudiero carries out his research at the US Salinity Laboratory, one of the USDA's Agricultural Resource Services national laboratories, and this is located at UC Riverside. With no further ado, I would like to turn it on over to our guest speaker. Elia, please take it over.
Thanks very much, Brandy. And I'm going to share my screen now and start the presentation over here. And this should be all right for all of you now, I think. Thanks very much for giving me the opportunity to speak to you all today about some of the research that me and some colleagues have been doing here in Riverside on the use of remote sensing imagery to detect, characterize soil salinity in agricultural soils so that it can be used for monitoring purposes and then as well for management of irrigation water in agricultural soils. First off, I'm going to briefly introduce the problem of soil salinity. We refer to soil salinity as the presence of major soluble ions in the soil. And most institutions, and well, especially us here in Riverside, use the electrical conductivity of a saturated soil extract, or ECE, as a means of measuring soil salinity. And this was developed by USDA at the mid 20th century as a way of measuring soil salinity. Basically, once we have a dried soil sample, we take it to the lab, and then we saturate it and extract the water from the sample, and then we measure the electrical conductivity of this water extract. And this has a very clear linear correlation with the amount of salts that are present in that solution. Therefore, this is like one of the most reliable ways for us to measure soil salinity. And by measuring it with this method, we can classify soils from non-saline to extremely saline. And we want note for people that might not be expert with this topic is that most of the crops that are commercially grown don't grow in extremely saline areas. Therefore, it's a very large interest for growers and for natural resource managers not to drastically increase salinity in the soils and maintain soils in the non-saline through moderately and less preferably to the strongly saline ranges of salt-affected soils. The one thing to say is that in irrigated agriculture, with salinity, for those that are not familiar with it, is controlled through irrigation, and basically it can be present through the soil formation processes, so already present in the soil, or it can be introduced via irrigation or other practices. The evapotranspiration process would make it so that salinity will accumulate at the top of the soil, whereas the irrigation events will push down the salinity. So that's more or less a brief description on how the system works in agriculture. And farmers normally slightly over irrigate their crops in order to keep salinity below the areas in the soil where most of the roots are, in order to minimize the influence that salinity would have on crops. Because as we see here in this graph, for some, let's take salt-tolerant crops, some certain levels of salinity are not detrimental to the crop, but once we reach a certain threshold that is different for different varieties of crops, but once we reach a threshold of sensitivity to salinity, the crop begins to lose yield, and therefore the profits of the farm will decrease as well. If we look at salinity globally, we have reports that puts it in the ballpark of 1 billion hectares of land to be salt affected. And what's important is that 20% of the irrigated farmland is estimated to be affected by soil salinity. And this is important because irrigated farmland, although it's very small in relatively speaking, produces almost half or 50% of the food that is produced globally. So if we take these 20% of irrigated farmlands that are affected by soil salinity, 50% of this land is found in 4 countries: China, India, Pakistan, and the United States. So this has been a problem that has been long known to affect soils, especially in arid, semi-arid Mediterranean environments such as California and the US Southwest as a whole. And since the beginning of the 20th century, USDA, and in this case for California as well, we're collaborating with the Agricultural Experimental Station of the University of California, there's been a consecutive surveys across the entire the whole state to characterize what the salinity levels were in agricultural soils, to understand how much agriculture will be limited in the different portion of the state. So this is a very interesting survey from 1918 that was carried out, as I said, by the USDA and the University of California around El Centro, which is for those not familiar with California, it's in the very bottom of the state at the border with Mexico. And you can see that even back then, before agriculture picked up very intensively, there were quite a few areas that were strongly affected and so on. Later on, during the 20th century, I think the NRCS changed their survey protocols for soil salinity, because being it a transit soil property, they stopped at some point measuring it in agricultural soil. So the tables that are nowadays present refer for most part to soils that are in non-irrigated land. Therefore, these reserves that I'm presenting today is in the context of providing reliable salinity information at very broad scales, also in those lands that are not covered by the traditional soil survey initiatives. So the type of data that we have for the US comes in forms of polygon maps, where we have all areas that are assigned certain levels of salinity. And of course, this is a map that we have in the corridor here at the Salinity Lab that was compiled in the 1970s. And nowadays, the successive iterations of the soil surveys from the different NRCS agencies across the US have refined the spatial representation of these maps. But the point being is that we don't have very much of a quantitative information present in agricultural soils. And this is more or less what we observe as well in the rest of North America, where salinity is also present as a problem and limiting factor for agriculture, such as the Canadian prairies in Canada. And even scarcer information is available for Mexico, where we have only a handful of publications that indicate that some of the agricultural areas of prime importance for Mexico are affected by soil salinity. So this is kind of an introduction to the problem. And now let's go a little bit closer to the actual soil property in the field and take a look at how it presents itself when we walk a site or we look at aerial imagery to try to determine what the status of soil spatial variability is. So when we go and look at the field scale, each field is managed differently by a farmer, so it might receive different quantity of water during the season, or have a different crop on it, or have different tillage and so on. But once we start looking at the field scale, we can see that there are quite a bit of short-scale, short-range spatial variability of soil salinity, and this is due to the presence of multiple influencing factors that affect how soil salinity is distributed across space, such as the soil texture, the soil type, and the type of irrigation management that each specific grower decide to apply in their field. And moreover, something to say is, like, when you look at this picture here and you clearly identify salinity efflorescence in the soil here, but most of the salinity, if you go and actually survey this field, would be found deeper down the soil profile, and is not visible in the soil surface. And this is because, as I mentioned a little bit earlier, in irrigated soils, most of the salts accumulate below the soil surface throughout the root zone. And we can approximate the root zone from like many of the agronomic crops that are grown in California to down to 1 meter. Sometimes they're like a little bit shallower, but sometimes also a little bit deeper. So let's just keep this as a reference from now on. So the one of the problems that we're gonna that I'm gonna discuss a little bit later as well is that there is a very little. There is not consistent way or reliable way to infer the root zone soil salinity from what it looks in the soil surface. So we need to find methods to be able to characterize the entire soil property at once, the entire soil profile at once, so that we can characterize the entire root zone and the presence of salinity throughout it. Then if we move at the multi-field type of scale, we can see that agricultural management is going to have a very strong impact on the outputs of soil quality. So here I have an example that I like to show of two pistachio orchards in Fresno County, and they are one south of the other. So left is north and right is south. They are of the same age, on the same soil unit, but they show drastically different outputs in terms of soil quality and crop yield, because the farmer in the south has access to water from the California aqueduct, whereas the farmer on the north is belonging to a different water district and doesn't have access to such good quality water, and whereas is using well water with that is rich in salts to irrigate their soils. Therefore, you can see that how from one field to the neighboring field, there's such a drastic difference that is due to management, mostly to the water quality that is used. And then, so you can start understanding that there's like a lot of contributing factors at different scales. And then if you zoom out at the very broad scale, you bring in the pedogenesis of the soils in a region, the geomorphology, the regional evapotranspiration and weather, that make it so that some areas in a valley, and then here I have the San Joaquin Valley, which is the southern portion of the Central Valley. Some area of the San Joaquin Valley, such as the Western San Joaquin Valley, is very rich in salts, whereas like the Eastern San Joaquin Valley doesn't have many problems of salinity at all. And this is due to to how the soils were originated to start with. So going further along, I mentioned a little bit about the surface soil salinity. Surface soil salinity can be mapped and monitored fairly reliably using satellite and aerial imagery, and it's pretty immediate because visually salt crust look so much different than the soil that they so that it's very easy to distinguish between the two. Unfortunately, though, as I mentioned before, there is some correlation, but very erratic correlations between what salinity is in the topsoil and what it is in the subsoil or throughout the entire root zone. Therefore, it is of little interest for agronomic purposes, for agricultural purposes, to map only surface soil salinity, whereas we have much more interest in mapping the full root zone. This said, mapping surface soil salinity is very important for limiting the environmental risks that are related to having a lot of salt crusts. And one like a clear example is for like air quality and water quality. in the Salton Sea at the moment, where we have like the playa that is with the Salton Sea that is receding. Here in Southern California, we have a lot of soil crust in the playa that gets eroded by the wind, and then they decrease the air quality in the region by a significant margin. Moving on then, one way to evaluate or model the root zone soil salinity is to go through the plant and its behavior and its performance on top of salt-affected soils. As I said before, plants' fitness or performance decreases as salinity increases. Therefore, we can use satellite imagery to map how plants are doing in order to understand how much salt they have been exposed to in the soil. So one way to do this by using vegetation indices, and with the proof of concept study that we've done was done on Landsat 7 at the 30 by 30 meter resolution using visible and near infrared bands. We evaluated several indices. You might have heard about the normalized difference vegetation index or NDVI or other or a landscape of other indices that perform fairly well altogether. But the one that was performing the best for California is this CRSI that we developed here at the Salinity Lab, and it looks at the near infrared and red reflectance and at the green and at the blue reflectance. With the idea that when you have a healthy plant, you would have a higher index, and when you have a stressed plant, you would have a lower index. But and what I'm going to say now is true for this index and for the others, such as NDVI. These indices are not a direct measurement of soil salinity. They are rather a relative crop stress, crop status indicator. So it's very good to identify stress crops versus non-stress crops. And this is because the visible correlates with the visible reflectance relates to the photosynthetic activity of the plant, and the near infrared relates to the plant turgor, so how much water is in the leaf. But at the same point, so just by using these near infrared spectral bands, it's very hard to differentiate between type of stress. This type of measurements also depends on the crop type. So if you have corn versus cotton, they would have a different spectral properties, and as well as the phenological stage. So when the crop is smaller, emerging from the soil, it will have a different spectral properties than when it's fully grown, and or when it's later on in senescence and it's dying out at the end of the season. And as well, when you're measuring this, you need to keep in mind that you are also measuring the influence of the underlying soil type that you might be flying your satellites over, so that you're always measuring some signal from the soil as well. And different soil types have different spectral properties as well. This to say that you can do these that we are talking about today with the thermal imagery too, and there's a nice example of it in this paper here. So as a sum up, when you're using satellite, a single imagery is not sufficient because you can't really rule out the presence of other stress. You're just measuring relative crop fitness. So we don't have a direct indicator of soil salinity, but some type of a relative indicator. And we need to reduce the noise from presence of other stressors or other influencing factors. And we do this by collecting a lot of ground truth and then developing data science models that can help us detect salinity in the big data that we're looking at. So the hypothesis that we worked on was that the multi-year time series analysis of remote sensing imagery can be used to model soil salinity levels and rule out other factors influencing crop reflectance. So this is done with the assumption that in irrigated, that is somehow backed up by observations that I'm showing here, that in irrigated soils, the fluctuations of salinity levels are very small in a short time frame. There might be a little bit of vertical movement throughout the season, but throughout the entire root zone, levels tend to remain fairly constant over a short number of years. And therefore, by considering therefore at a single location the root zone soil salinity to remain fairly stable, we can use multiple years of remote sensing data to find the best time in this time series that best correlates with salinity as measured on the ground. So this is what I just said here in graph before. So the way that we go about it is by creating this time series and then looking at the year that has the maximum performance at any of the locations across the study area. And the idea is that we have presence of transient stressors, so water stress, pests, mismanagement from the farmer, couldn't have enough water availability to fully irrigate the site and so on. Transient stressors that are supposed to be there 1 year they're there, 1 year they're not, and such. Whereas we have a more permanent stress, such as salinity, that is constantly there over time. And therefore, the relative crop performance is limited by these transient stressors and the permanent stress that is salinity. So if we take the year with maximum performance, we minimize the presence of the transient stressors and can relate the relative crop performance to the levels of salinity in the soil. So we test this out in the Western San Joaquin Valley in California, which is known to be salt affected, one of the most salt affected areas in the state of California. And to do so, first off, we went out to get a lot of ground data to calibrate and evaluate our models. And to do so, we used the protocols that for field scale soil salinity mapping that developed by Dennis Corwin and other people at the US Salinity Lab throughout the past 3 or 4 decades. The procedure is stepwise, but fairly easy to understand. We measure soil spatial variability with soil sensors. In particular, we use the apparent electrical conductivity sensor measurements. And then based on the spatial variability that we capture with the sensor, we identify a few locations that are representative of the entire site where we go and do the soil cores. We do the soil sampling, then we do the soil laboratory analysis to characterize salinity. And then there's the part where statistics kicks in, and we use these ground measurements and the sensor measurements to make a model so that we can estimate the soil properties that we are measuring in the lab throughout the entire field. And at the end, we basically create the soil map. And this soil map can be used gridded out with the same grid that the satellite is recording their imagery, but this can be used as a ground truth for calibration and evaluation of the models that we are developing with remote sensing. So we did this procedure at 22 fields in 2013, and the Western San Joaquin Valley. We acquired over 42,000 soil apparent conductivity sensor measurements that were used to identify a representative location where to do soil sampling. And we measure several soil properties, but we are focusing, of course, on salinity, ECE, on the 0 to 1.2 meter aggregate that we call the root zone. And with these, going through the regression modeling and mapping the salinity at the field site, we come out with over 6,000 grid cells that can be used for ground truth. And these cells have an accuracy of 93%. So we test the idea of using the multi-year maximum of the vegetation indices, and here's Riverside, and you can see that this multi-year maximum always performs better than the cherry-picked data from the year with the best correlation. So having this multi-temporal type of approach always pays out here in California. But then this is not enough to produce a reliable map. So we add other covariates such as the crop type, meteorology, soil information from Surgo, and information from the management that is done at the fields to get a more accurate model that can then be used to extrapolate salinity values across the entire region using the remote sensing and the other covariates that we are using. And here we have the ground truth salinity, so what we measure in the field and what the model estimates. And the closer you are to this one-to-one line, the better. So we can see that the model is fairly accurate in predicting salinity across a fairly wide range. He has some troubles with fallow fields in the low salinity ranges, but for crop fields, it's performing pretty well. So before we can produce a map we need to do some model evaluation. And so we have a paper here that talks about, that walks through about all the evaluation steps that were done for this model, including the cross-validation that comes with most of the literature data science techniques that are used for this type of modeling. Then we also use independent soil sampling. We took the map and said, compared it to the classification of soil crusts to see if the soil crusts were present in areas that were otherwise classified as affected by high salinity. And then we have this analysis done with different types of satellites coming at different resolution and comparing how this data looks alike if you are using different satellites. And then as well, we are something that we don't present in the paper. We've done a lot of research in orchards as well, where we have a different type of ground cover from the crops, and observe that the specific techniques that we use for agronomic crops doesn't yet perform very well in orchards, and that's something that we are currently working on over here. And then one thing that we always do, and that is very important, is to connect to the stakeholders and go and ask a grower, show them the map, and then most often they would have a handful of soil samples for each of their fields that they know that is most affected by soil salinity. So you can show the map and compare it to them, and you can see that. But in this specific case, we have very good match between what we observe with the satellite imagery and what the grower is measuring, with the exception that we have much better information from remote sensing, because we are able to disaggregate spatially the information, so we can identify areas in a single field that are higher salinity than others, ones that might have lower salinity. So here's the map. You can contact me to have a higher resolution version of the map if you're interested. We present the map in this California agriculture paper from 2017. But then what we are using this for nowadays is to try to inform to do crop yield projection and try to inform growers on what water they should use to better manage crops at their sites, given the starting levels of salinity that they're dealing with. And as well, we are this can be used to take a look at the land use changes and the effect of these changes over soil quality over time. And there's one example that I can give you today on the water management induced land use changes and salinity in the Broadview Water District in Central California. This was a very productive water district in the 90s and early 2000s. But then in mid 2006, they sold the water rights and to another water district, and then they followed all the fields. So you can see that from being very productive, it went to a few years later to be pretty much bare land where nothing can grow really, because most likely because of higher levels of soil salinity. And this is reflected by the survey, a survey that we did that the Salinity Lab did in the air in 1991, and compared to the remote sensing predictions that were from 2013. And what we can see that, you know, total changes of salinity increased of 43%. And what's like most relevant here is that all the very good quality soils that were non-saline and slightly saline soils in 1991 have become moderately and to strongly saline in 2013. So in a span of 20 years, or so, the quality of soil degraded by a very significant extent. So what are the limitations and research gap of this technique? We have uncertainty of prediction of low salinity values, and farmers are specifically and especially interested in predictions of low salinity values so that they can better target the crop selection for their sites. So this at the moment is not satisfactory there, but it's still like much better than anything that was available before. The reflectance of salt tolerance crops that grow in fallow land is problematic because they do poorly at low salinity, then they do better at a slightly higher salinity, and then when salinity becomes very extreme, they start doing poor again. So this type of salt tolerant crops, they do poorly at low salinity and at high salinity, and they only do better at mid salinity. So it's very hard to understand their their fitness through remote sensing and what it's due to. So there's not much work done on tree crops, and that's what we are focusing on. Then we are testing how to better introduce different types of source data from remote sensing, including thermal, to improve the mapping method. And as well, we need to better define what root zone and what it means and what the depths is that we are actually mapping this salinity at. So we need to have a better inclusion of information of soil and management in our models. The other thing that we want to say is that this approach for multi-temporal canopy reflectance is not a universal approach for remote sensing of soil salinity. And as a matter of fact, some researchers in China took what I did and they adapted to the problem of heavy metals in soil, which are the same type of temporal consistency in soil. So they're using the same type of algorithms that I created to map heavy metals in soils in China. So moving forward, what we saw is that we can do reliable and accurate remote sensing of soil salinity at agronomically relevant levels of soil salinity. And we need further research to improve these predictions. And we are working on more sophisticated methods with data science, with the AI and machine learning at the moment. And we are also collecting all the historical data that was collected in California, Arizona, and other neighboring states nowadays, from the 70s to present, to take advantage of the full availability of remote sensing data from NASA in order to create a spatial temporal model that can tell us how salinity changed throughout time for the US Southwest. And that's what I'm doing with this current grant that is funded by NIFA AFRI. So with this, I'm done. I'm putting here like the two major references for the research that I talked about today. Don't hesitate to contact me to get copies of this. And here's the reference to the grant that is currently financing the research. My Twitter handle, if you want to follow what we do in my lab, and as well the website for my lab, so that you can follow what me and my team are doing at the moment. With this, I'm done, and thanks very much for your time.
Thank you very much. All right, so we will now open the floor for anybody with questions. There is a feedback.
Randy, there is a echo.
A feedback, yes.
Yeah, I don't know whether it's a phone and also computer. Oh, both of them are on.
I agree.
Yeah, I think it's now.
Okay, very good. All right, thank you for that, Kabir. Opening it up for questions. If anybody has a question you'd like to ask in person, please raise your hand, or if you'd like to type it into chat, we will address those also. So I'll give it a second, and then there's a couple in chat.
I have a question for Elia. This is Kabir. I also work, with everybody here, Brandy, Phil, and whole groups. And question is, are you also putting like saline soil or sodic soil, or also saline sodic soil? Are you putting all three of them in one place, or just considering about the saline soil? So its microphone is off, mute, actually. Elia.
Yeah, I got it. I was muting, because I thought that the feedback earlier on was coming from me. Thanks. Thanks very much for the question, and it's very, very relevant for many of the soils in California. So at the moment, we have done what we publish is only on the electrical conductivity, so just salinity. But we are looking into integrating available soil pH maps and the ground truth salinity information that we get and other ground information that we are collecting in order to create sodicity. Like I have an indicator for sodicity as well in these maps that we produce. Because at the moment, as you may imagine, from satellite imagery, the sodicity would have a very like a compounding effect on crop performance. Therefore, it's like it is also being picked up by the satellite imagery that we are using. But yeah, but as I said before, we just started with the electrical conductivity, and we are moving to sodicity for future research and ongoing research, as a matter of fact.
Thank you. And so you mentioned about like 1 billion hectares of world lands are saline. That's not part of the sodic or saline sodic soil, right?
Well, so that's like FAO estimates on salt affected soils. No sodicity in there, I think, but that's relying on each country's national surveys. But this is, as I said, the most surveys are done on non-agricultural soils. So like agriculture in salinity non-agricultural soils is much less of a dynamic problem that it is in agricultural soils, where we can add and remove salinity with irrigation and fertilization and such. So the actual numbers are not that accurate. So I would assume, well, I'm not going to give an educated guess, but the problem is that these numbers that FAO and other repositories have a very big uncertainty to them, because of the fact that we don't have global scale methods that are accurate at the capturing salinity in managed soils.
Thank you.
Thank you.
All right, we have a couple of questions in chat, so I will ask those. In the future, do you imagine you will use hyperspectral data at all?
Well, yeah, we have done some trials in the past with hyperspectral. We are using it nowadays on some of our research with our collaborators from USDA that have it mounted on UAVs to do like short scale type of research on like a field scale and such. But what we've noticed is that there's not like a very clear signature for salt affected characteristics throughout the plants. You may be able to use hyperspectral to go directly into the soil, but then again, you're not looking at the full soil profile. So there's a lot of noise in the measurements on hyperspectral as well, due to other influencing factors that are not only salinity, that are influencing how crop grows over different soils. So yeah, it provides more data, but at the moment, what we are getting is from multispectral is satisfactory at the moment. We want to make sure that we are including more comprehensively other covariates that might help us and better characterize the spatial variability of salinity across different spatial structures, rather than improving the power of the main predictor that is remote sensing.
Great. Next question. Is there any intention to improve index or modified index for salinity in the future?
Well, as I said, like I am, my philosophy is that I'm kind of a soft mechanistic type of person in the sense that I'm well aware that we are measuring physical processes with these tools, but I'm also very well aware that there is a lot of random spatial errors in any of the measurements that we are taking. Therefore, I'm more interested in personally in developing data science methods that can help us removing the random error that is just putting noise in our data, rather than improving the physical fit of a specific index with the target variable. But indeed, there is a lot to be done still in that field, and there's quite a very good and competent researchers around, well, here in the States and as well around the planet, that are doing very good work in testing new indices from aerial and satellite imagery, both on multispectral and, as we were mentioning earlier, on hyperspectral as well.
Thank you. We have two hands up. One, Daegu, your hand has been up for a while. Did you have a question?
This is Blake. Hello?
Yes. Hello, Blake. Go ahead and ask your question. Thank you.
Yeah, I knew at this Microsoft Zoom kind of thing. Anyway, I raised my hand and hi, Elia. This is Blake.
Hi, Blake.
Yeah, I wanted to ask you. You put up a very impressive graph showing the regression between CRSI and the ground truth salinity that had an R squared of 73%, but it, you know what, when you, that 73% R squared happens because you got samples all the way out to 35, maybe 38 EC. And I was curious, when you get down to the realm of, you know, basically 1 to 8 decisiemens, which is no problem, up to, oh, not good for most crops except pistachios. What is the future of this approach within that much more narrow range of management requirements for you know, our successful crop production?
Mm-hmm. Well, so yeah, thanks for noticing that, Blake, and like very nice to see you here. As you said, like, yeah, we have a very goodness of fit of the model, but it relies on data that is on the higher range of salinity, which is still like not like some people around the world would judge that like 30 and 40 decisiemens is still fairly low for the values that they might be measuring in let's say places like Iran, where I saw saturated basis tracks in the hundreds. Anyways, we do have like in the papers that we published, and so I can show it to you in another call if you want, but we do have an analysis breaking down by salinity classes, and we are doing fairly well above 4 decisiemens in being able to determine what the salinity is actually on the site. Anything below 4 decisiemens, you happen not to have any response from the crop at all, and therefore you're not capturing any variability of it from the model. But those are levels of salinity that you know are not too much of a worry for growers, which are more interested in the critical. We say like between like around 8. You don't want to go above 8, so you want to keep everything below that in order not to lose your crop in your fields. But to better improve this information, we need better covariates. Something that I didn't show here is that when you add reliable soil texture information, so clay and sand content, the fitness of this relationship increases even more. Unfortunately, though, we don't have a specially disaggregated product that is accurate enough to be able to apply that relationship to the entire state of California at the moment. But if we had better soil texture measurements, we would be able to improve even more the accuracy at the low salinity ranges for most of the crops that are used nowadays.
If I understand you correctly, though, that as a survey tool, since you're getting good response and relationship with the CRSI for salinity above 4, then this can still be a good resource to give me that spot shot analysis. If I'm farming 10,000 acres and I find those areas with that, you know, over that definite threshold, then I know where to go and look and do some remediation.
Yeah, yes, correctly. And as a matter of fact, if you saw like that farm map that I showed like in one of the last slides, where that had salinity from 0 to 12, and we identified the average salinity for the field with the spatial variability at this farmer's field, pretty much on point. And those were not fields that we used to calibrate the models. We just went to the grower, and the grower had these measurements that they did, and we just paired it to what the map was predicting, and it was pretty much on point.
Great, thank you.
Yeah, thank you.
All right, we have one more hand up. Degu, your hand has been raised for a while. Did you have a question? All right. Couple more in chat here. You did mention, Elia, that you do not include tree crops. Is that something you're intending on doing in the future?
Yeah, like we have a grant that is from NIFA that we are currently investigating this, and this is a problem that we stumbled upon when we were developing the first like the proof of concept for this method. And basically, it's very hard to characterize salinity in orchards, especially those that are irrigated with drip irrigation or micro irrigation, because the spatial patterns of soil salinity there are very, very remarkable in a very short scale. So within like 6 feet from the dripper, you have like a wide ranges of soil salinity. So it's very hard to first characterize the salinity, but then understand how much of this salinity is actually affecting the tree, and therefore then relate that to what you're looking with the satellite images. But we are currently ongoing field experiments, field measurements, and as a matter of fact, I'm very happy to see Blake here, because we have been working at some sites where him and the colleagues from UC Davis as well have been working on pistachio, and we are working on citrus as well now, and almond, to try to understand how to best characterize salinity in these systems, to then use these field characterizations to calibrate our remote sensing models. But yeah, it's on the works. It's not very trivial. It's pretty hard to do at the moment.
I can imagine. Yeah, I could see in our county, we're in Colusa County, and a lot of our acreage is the orchard. So that would be pretty useful for us up here. In the same vein, this next question: which crops can you most accurately measure the salinity using the methods that you've been using?
So, well, as we were mentioning earlier on with the previous question from Blake, we are very good at measuring crops that are grown in the 4 to 12 decisiemens range, or a little bit higher, which would include cotton, alfalfa, and a few others. The thing is that growers have a general sense of what the salinity levels are in their field. They don't have like the spatial variability information knocked down very well, but they do have a certain idea of what the levels are in their site. So they don't put like a so sensitive crop in lands that are slightly affected by salinity. They would put crops like alfalfa that grow well with a slightly higher salinity levels. So we are not doing very well on salt sensitive crops at the moment, because the inherent problems that come with this type of approach that we are using.
Great, thank you. All right, this is the last call for questions. So we will give you another couple minutes here if you've got a question and you want to throw it up in chat, or if you want to raise your hand. I would also like to point out that I have shared my screen, and you can here find the contact information if you have any follow-up questions that you haven't been able to address today, or an afterthought And then also, this is our chapter contact, and also inviting you to look at our posted webinars on YouTube, our California Nevada chapter YouTube channel, and then look for us on Facebook. Join so you could be part of the conversation and be aware of all of the happenings. All right. So last call for questions. Going once. Going twice. Okay, on behalf of everybody with the chapter, Dr. Scudiero, we would like to say thank you very much for your time.
Thanks very much.
And your presentation. Yes. Thank you. Bye, everybody.